Good morning. Today we'll see some problems. How the problems on the Carnot cycle are being asked and how to solve those problems. Okay. And this is this is P. Venkata Mahesh, Assistant Professor in Mechanical Engineering Department, Institute of Aeronautical Engineering. So the course is Refrigeration and Air Conditioning. It is for 7th semester Mechanical Engineering students. And as I said, the topic which we are going to discuss today is how to solve some problems related to Carnot cycle. So this is the first problem. As we have discussed already, we'll just recap what is a Carnot. What is a heat engine, what is a refrigerator, and what is a heat pump. So suppose same machine can be working as the three ways, whether it can be a refrigerator or it can be a heat pump or it can be a heat engine, provided it is working based on Carnot cycle. Okay, if it is working based on a Carnot cycle, the same machine can work as a refrigerator or as a heat pump or as a heat engine. So that is the reason the problem it is said that the machine working on a Carnot cycle operates between 305 Kelvin and 260 Kelvin. Calculate the COP when it is operated as a refrigerator, as a heat pump or as a heat engine. So the same machine can work. So this point we should keep in mind. So same machine can work as a refrigerator or as a heat pump or as a heat engine, provided it is working on Carnot cycle. Okay. Now we'll just recap what is this setup. This is a high temperature reservoir and this is our engine machine, and this is a low temperature reservoir. So what happens is, if I provide a work, okay, if I provide work input, work net, this machine can work as a refrigerator or heat pump. So what it will do, it will take some heat from the lower temperature reservoir, and it will give heat to the higher temperature reservoir, and this heat is nothing but QL plus W net. Okay, QH is equal to QL plus W net. So this is the net work that is supplied to the engine. Now the process is like this. It can be a refrigerator or a heat pump, provided where is our attention is. So suppose our attention is to heat the room, then it is a heat pump. Or if our attention or if our requirement is to keep the room cool, then this is our room and this is atmosphere, and in this case it can be a refrigerator. Okay, so this is the now what about the heat engine? So heat engine is the reverse of this, and it is it takes some energy from the high temperature reservoir, some heat from high temperature reservoir, and it gives part of it to the low temperature reservoir, and the remaining will be given as work output. Okay, so heat engine gives some work, and refrigerator and heat pump takes some work. Okay, so that is the only difference. Now difference between refrigerator and heat pump is, if the lower temperature is to be maintained in the room, then it is a refrigerator. If higher temperature is to be maintained in the room, then it is a heat pump. So that is the basic difference between refrigerator, heat pump and heat engine. Now coming to solving this problem. So this is the name of the cycle, Carnot cycle, is mentioned because when we want to solve this problem, if Carnot cycle is mentioned, directly we can take the COP in terms of the temperature. That is the reason we can specifically it is stated as Carnot cycle. Okay, if it is Carnot cycle only, then only you can write this COP formula in terms of temperature. Okay, now, so what is given in the question? The machine is being operated between two temperatures. One is 305 degrees, this is 305 degrees, and this is 260 degrees. So this is a higher temperature and this is a lower temperature. So higher temperature reservoir TH is equal to 305 Kelvin, lower temperature reservoir TL is equal to 260 Kelvin. So that is one thing that is given in the question. Now, if it is working as a refrigerator, so the first objective is refrigeration, or keeping the room cool. Okay, keeping the room cooler than the atmosphere. So the main the purpose of the refrigerator is how much heat it can take from the room and reject to the atmosphere. So the numerator is QL. QL is how much heat it can take from the room which is to be cooled, and this is W net is the amount of work that is supplied to the the refrigerator. So it is QL by W net. And what is this W net? As we already discussed, it is the difference between heat taken from the cold room and the heat given to the atmosphere. So here it is giving more heat to the atmosphere than what it is absorbing from the cold room or cold storage place. Okay, so the same thing can be expressed in terms of temperatures, and it is like this. Now, TL, the lower temperature reservoir temperature. So the lower temperature is 260 Kelvin and the higher temperature is 305 Kelvin, and the lower temperature again it is 260 Kelvin. So here directly they have given in Kelvin. Say suppose if they have given in centigrade. Okay, say suppose they have given 20 degrees centigrade and 5 degrees centigrade, something like that they have given. Then what we have to do? We have to add 273 to these temperatures and make it Kelvin before we substitute in this formula. So that is the precaution that we have to take when we are solving these problems based on the Carnot cycle. Okay. Now here, if I simplify this, the simplification process is very simple. It is 260 divided by 45. Then it is 5.78. So the simplification is very simple. Everyone can do. The only thing is what should be there on the top and what should be there on the denominator. What should be there on the numerator and what should be there on the denominator. So if it is a refrigerator, the numerator is the amount of heat taken from the cold room. Okay, cold space. The amount of heat that is extracted from the place which is to be maintained cold or cooler than the atmosphere, because we are giving to atmosphere. Okay, so the room is cold and atmosphere is also you can say it is also cold, or it can be higher temperature. The temperature of the room is lower than the temperature of the the atmosphere. So in summers, what we will do, we'll have a AC inside the room, and outside, or you can say if you take a cold storage room, you are storing some fruit inside the room and outside temperature is very hot. So in such cases, what we will do, we'll extract some heat from the cold storage room and reject to the atmosphere. But there is a tendency for heat to come back, tendency for a heat to flow from higher temperature to lower temperature. So that is the reason we need to insulate the cold room so that the heat transfer is negligibly small. Okay, or it is an acceptable limit. Okay, so here our point is, if it is a refrigerator, the numerator is the amount of heat taken from the cold place. or cold reservoir. Now coming to the second point. The second point is a heat pump. So what is the heat pump doing? It is taking heat from the cold place and giving to the hot room. Okay, say suppose I am in Canada and outside everything is snow, so I cannot stay comfortable in the snow. So what I have to do, I have to take heat from the atmosphere and supply to the room so that the room is hotter and comfortable. So the numerator is how much amount I can supply to the hot room. Okay, because here it is heat pump, heat is being pumped, so the amount of heat pumped to the hot room is our objective. So the amount of heat supplied to the higher temperature reservoir divided by work net gives me the COP of the heat pump. Now COP of heat pump, or it also called as energy performance ratio. What is that? EPR. Sometimes they will ask in question EPR. It is energy performance ratio, coefficient of performance or energy performance ratio. This is a heat pump, not HEM. So energy performance ratio or COP of a heat pump is calculated like this. So what is the thing we should take care? The amount of heat supplied to the hot room. Okay, amount of heat supplied to the hot room or higher temperature reservoir should be our the requirement. So this is QH divided by work net. So that is giving the COP. And as we have already seen, this is 5.78 and this is 5.78 for refrigerator and 6.78 for the heat pump. This we have already seen. So if at all this COP of heat pump is there, then 1 plus COP of refrigerator. So this problem is giving a proof for this statement. Okay, COP of heat pump is equal to 1 plus COP of refrigerator. So this is a simpler way you can calculate. If only COP of heat pump is asked, you can calculate like this. If both are asked, COP of refrigerator and heat pump, then you can find out COP of refrigerator, add 1 to that, you will get a COP of the heat pump. So that is the second part of the problem. So what is the third part? It is the heat engine. So what is this heat engine doing? So the heat engine, the aim of the heat engine is to supply some work. Unlike the refrigerator and heat pump, the heat engine, what it is doing is, it is taking some heat from the higher reservoir and supplying part of it to the lower reservoir, and the remaining part is supplied as some work net output. So that the COP or efficiency of the heat engine is nothing but the amount of work which it can supply. Okay, the amount of work that can be produced by the heat engine. Now what is the input? The input is the amount of heat taken from the hot reservoir. So it is taking from heat from the hot reservoir, that is the input, and the output is the amount of work that it can supply. Okay, so to avoid, we will just redo once again so that it is very clear. So what is the output or the required thing in case of a refrigerator? It is the output is the amount of heat removed from the cold room. What is the input? It is the net work done on the engine or net work supplied to the engine. If I come to the heat pump, the amount of heat supplied to the hot room, that is the output, and the input is the work done on the engine. Okay, or work supplied to the engine. And coming to the heat engine, the output is the amount of work the engine can supply, and the input is the heat supplied to the engine. So these are the three things that we should we should remember. If I remember these three things, any problem based on refrigerator or heat pump or heat engine based on Carnot cycle, it is easy to solve. So this is about the first problem. We will see two more problems and we will close the session today. Now, the Carnot refrigerator. So this is the second problem. The Carnot refrigeration cycle absorbs heat at 270 Kelvin and rejects heat at 300 Kelvin. Here also the temperature is given in Kelvin. So it is very easy. It is simple. No, we don't have to add any 273. If it is in degree centigrade, then I have to add 273 and make the temperatures into Kelvin. So this point should be, we should be very careful. What is the units of the temperature? The units of the temperature must be in Kelvin for this kind of problems. Now, first bit is calculate the COP of this refrigeration cycle. Okay. So, what is the COP of the refrigeration cycle? It is very simple. What is that? Refrigeration. As soon as refrigeration comes, what should be the numerator? Numerator is lower temperature divided by higher temperature minus lower temperature. So this is the COP formula for a refrigerator. Okay. Now what is the next bit? It is if the cycle is absorbing this much heat, okay, at 270 Kelvin, how much kilojoules of work required per second? So this is the second point. So the heat is being absorbed at kilojoule per minute. Okay, 1130 kilojoule per minute. So we need per second. So kilojoule per minute is to be converted into kilojoule per second. So what I have to do? I have to divide it with 60 because 1 minute is equal to 60 seconds. If I do that, I will get this seconds. Now, if the same thing operates as a Carnot heat pump, what is the COP? If it is a heat pump, again, the higher temperature divided by TH minus TL. So, this is the COP for heat pump. Now, what is the fourth bit? How much kilojoule per minute will the heat pump deliver at a higher temperature if it absorbs this much heat from the lower temperature? These are the four questions we have to solve. So what is given? The higher temperature is given and the lower temperature is given. Higher temperature is 300 Kelvin and lower temperature is 270 Kelvin. What we have to do first? First we have to find COP of the refrigerator. As we have already discussed, COP of refrigerator, the temperature of the lower reservoir to be on top divided by the difference in the temperatures. So if I do that, it is a 9 COP. Now what is the second bit? What is the work required per second? So what is the work required per second? It is again, this we know because heat absorbed from the lower temperature is given. So the heat absorbed from lower temperature is QL and W net ratio, if I do, that is also equal to COP, and COP is equal to, already we have calculated 9. So COP is equal to QL by W net. If I manipulate that, what I can get is Q net is equal to, Q net will go there, COP will come here. It is a QL, heat absorbed from the lower temperature divided by COP. What I will get is 2.1 kilojoule per second. So the calculations are very simple. You can do it. Only thing is you should understand the concept. So what is the concept? The COP of refrigerator means the heat absorbed from the lower reservoir divided by the net work done, and or it is also equal to the temperature of the lower reservoir divided by the difference in temperatures. So either of the formulas will give the same answer, and that is the answer is given here. Now what is asked what is the work? What is the work required to remove CQL? So if I use this formula, I can manipulate and find what is the work required for the refrigerator to extract this 1130 kilojoule per minute. Okay, this much of energy is required by the refrigerator to extract this much energy from the cold room. Okay, or lower temperature. So it is TL here. It is a lower temperature reservoir. Okay. Now what is the next bit? Next bit is what is the COP of the heat pump. As soon as I said heat pump, or as soon as the question says heat pump, what should we remember? We should remember that the aim is to supply heat to the room, hotter room. The aim is to supply heat to the hotter room. So the hotter room is at a TH, higher temperature. So this divided by TH minus TL will give the COP of the heat pump. So if the COP of heat pump is known, so what is the temperature? It is 300 divided by 270, 300 minus 270, that is equal to 10. So this is a straightforward once you have given this formula. Once you understand what is the formula to be used, substitution and simplifications are very simple. So I am mostly focusing on explaining the concept rather than simplifying the values. Okay. So the concept is the amount of heat to be supplied to the hot room. So higher temperature divided by the temperature difference. So this will give the coefficient of performance of heat pump or energy performance ratio, EPR of heat pump. So EPR, energy performance ratio, or COP, coefficient of performance, both are same. Now that is the third bit. What is the fourth bit? It is said that the heat, he is asking what is the heat delivered. So what is QH? QH, or heat supplied to the hot reservoir. So what is that? How to get that? If I know what is the COP, okay, if I know what is the COP, I can substitute in this formula and tell what is the heat supplied to the hot reservoir. He has already given what is the amount of heat absorbed from the lower reservoir. So the amount of heat absorbed from the lower reservoir is 1130, and what we have to find what is the amount of heat supplied to the hot room. Okay, so if that is the case, COP is we have already calculated for heat pump, it is 10, and that is equal to QH by QH minus QL. If I substitute the QL, energy extracted from the lower reservoir, it is QL, and that if I substitute and if I take 10 COP that we have obtained here, and I can find out what is QH, amount of heat supplied to the higher reservoir. So amount of heat supplied by higher reservoir divided by the net work. Net work is nothing but it is difference between heat absorbed and heat rejected. So if I do like that, what I will get? I can simply find what is the energy supplied to the heat pump. Now you can see here, it is the heat taken from the lower reservoir, and this is the heat supplied to the higher reservoir. So the hot room, we can supply this much heat with what is the work required, the difference of these two. What is the difference? It is 126 kilojoule per minute. So if I simply use heater, it will supply only this much heat to the room. Okay. If I use the heat pump, what it is doing? It is supplying so much additional. Okay, it is supplying additionally 1130 kilojoule per minute with the same energy input to the heat pump. So this is the advantage of using heat pump instead of a heater. Okay, so if I use a room heater, if I have to supply this much heat, what I have to do? I have to give so much of work in energy supply to the heater. Okay, but if with the heat pump, just if I supply only this much heat, I can give, I mean, this much work or this much energy to the heat pump. I can supply this much of heat to the hot room. So this is the advantage of using a heat pump instead of a simple room heater. So this is the second problem. Now we will see the third problem. So here there are two refrigerators, A and B. Okay, this is refrigerator A and this is refrigerator B. So they are working in series or operated in series. They are being operated in series. Series means the lower reservoir, next higher and next higher. So this reservoir is having temperature more than this. This reservoir is having temperature more than this. And what it is saying, the refrigerator A absorbs energy. Okay, what is the amount of energy? 1 kilojoule per second from the body at a temperature 300 Kelvin. So this TL is equal to 300 Kelvin. Okay, and rejects as heat to a body at a temperature T. So this temperature is given as a T. The temperature is not given. So the refrigerator absorbs the same quantity. Whatever heat this machine is rejecting to this the intermediate reservoir, the same energy it is absorbing, and which is rejected by this A is rejecting some heat, and this is equal to the amount of heat extracted by the machine B from this. So this both are equal. So that is the one statement given. And rejects heat to a body at a temperature 1000 Kelvin. So this temperature is also given. It is 1000 Kelvin. So the highest temperature is 1000 Kelvin. The lowest temperature is 300 Kelvin. The intermediate temperature is not given, and you have to find out what is the intermediate temperature. So if both refrigerators have same COP, so this is another condition that is required, that is given. So the COP of machine A and COP of machine B both are equal. So this is one point given. COP of A is equal to COP of B. So this is one point given. And what else is given? QB. Okay, QA rejected, amount of heat rejected by A is equal to amount of heat taken by B, and that is we have taken as a QM. Okay, so that is one condition. Two conditions they have given, and they are asking what is the temperature of the body B. So this temperature we have to find out, and we have designated it as a T. And the COP of the refrigerators, both refrigerators are having same COP. That COP I have to find out. Now what is the rate? The rate at which energy is rejected to the hot body. Okay, rejected as heat to body at temperature 1000 degrees centigrade. So this amount of, what is this amount of heat that is being rejected? That I have to find out. So these are the three things I have to find out. So I will take this diagram and I will move forward. So here this temperature is given. This is 300 Kelvin. This temperature is given. This is 1000 Kelvin. And this temperature I am taking as T. And what else is given? This heat rejected by this machine A is equal to heat taken by the machine B. Okay, so that is also given in the question. Now what else? I have to find out. I have to find out what is T. So what is else? What else is given? COP of A is equal to COP of B. Now both are refrigerators. So both are refrigerators means what should be the numerator? The numerator must be the temperature of the lower reservoir. So between these two, 1 and 2, between these two, the lower temperature is TL. So it is TL by the difference between these two, and that is equal to Tm minus TL. So this is the COP of A. Again, this second one is also a refrigerator, and if I consider between these two, the lower temperature is Tm divided by Tm minus Th minus Tm. So this is higher reservoir and the intermediate reservoir. So if I use like this, what I can find out? I can find out what is the temperature T with some manipulations. So the manipulations are given here. It is very simple, provided if I can arrive at this equation. Okay, this arriving at this equation is very important. Unless I understand the concept, I cannot arrive at this equation. So what is the concept again? We have two reservoirs. This is 1 and 2. Between these two, the lower reservoir temperature is on top because it is a refrigerator, and the denominator is a difference between these two temperatures. Now, between these two reservoirs, the lower temperature is this one, and that is the numerator because it is a refrigerator, and the denominator is the difference between these two temperatures. So if I do like that, I almost have come to the solution, because if I come here, it is very simple. 300 by T minus 300 is equal to T by 1000 minus T, because both COPs are equal. And if I cross multiply this, I will get 300 into 1000 minus 300 T, and if I cross multiply this, it is T square minus 300 T. Now this is 300 T, this 300 T will get cancelled. Now what is the T? T is equal to root of 300 into 1000. So that is equal to 547 degrees, 547.7 Kelvin. So this temperature we have found out, and it is equal to 547.7 Kelvin. Now if I substitute this formula, this value either in this or in this, I will get the COP of the two refrigerators, both are which are equal. Okay. Now what is the value? I am substituting here, and this is 300 divided by 547.7 minus 300, and I am getting COP as 1.12. Even if I use the other formula, what is the other formula? 547.7 divided by 1000 minus 547.7. So even if I use this formula, I will get the same answer, because I have equated these two and I got this value. So either I can use the 547.7 divided by 1000 minus 547.7, or I can use 300 divided by 547.7 minus 300, and I will get the value as 1.12. There is no units because it is a numerator is temperature, a Kelvin, and denominator is Kelvin. So I don't have any units here for COP. So that is a important side point that we have to remember, because both numerator and denominator are having same units. It is a dimensionless quantity, COP, or efficiency, or energy performance ratio. So all are having no units. Now the another bit, third bit, what is asking is the rate at which heat is rejected to the body at 1000 degrees Celsius. So I have to find out what is QH. So if I want to find out what is QH, how to find out? There are two ways. One is the formula of COP of P is equal to Q, this is refrigerator, so it is QM divided by QM minus QH minus Q. Okay, so this is one way I have to find out. But what is QM? I don't know what is QM. So how to find out QM? I have to use this formula, and that is equal to COP of B, and this is equal to QL by QM minus QL. Okay, so if I use these formulas, I can get these answers. Okay, so in the textbook, if you see, they have given in this manner. Okay, and this is also a valid answer. So what I am doing here is I am using first finding what is a QM. For finding what is QH, I have to first find what is a QM. Heat rejected by the body A or heat absorbed by the body B, both are equal. That QM I have to find out. And he has given what is a QL. QL is given as 1 kilojoule per kg Kelvin. Okay, that is 1, that QL is given. So if I know what is QL, what is the formula? 1.12 is equal to QL. QL is 1 divided by QM minus Q minus 1. So if I do like this, again I will get the same answer. So what I will get if I multiply this here, it will be equal to QM minus 1 is equal to 1 by 1.12. So this is this value. So it is equal to 0.826. So this QM now is equal to 0.826 plus 1, and that is equal to 1.826. So we should not get confused why in the textbook they have given like this. Okay, so what is the, either I can use directly the formula of COP, or I can find what is the work and then find what is the heat rejected. So either way I will get the same answer. Now this is, now I know what is a QM. QM is found out. What I have to do now? I have to find out what is a QH, that is supplied to the hot reservoir. So again I can use the same formula. What is that? 1.12 is equal to QH. Here it is QM divided by QH minus QM. Okay, in between these two, this is the lowest temperature. So it is that I am taking on the numerator. Okay, so the concept is, if it is a refrigerator, the heat extracted from the lower reservoir should be on top, or the temperature of the lower reservoir should be on the numerator. Okay, the denominator is the difference between temperatures. If I am using temperatures, or if I am using heat, it is the difference between the heats between these two reservoirs. So that is the important thing that I have to remember. So the remaining manipulations, how I did, that is not a big thing. Okay, now if I do like this, what I am getting here, I am getting QH minus QM is equal to, what is QM? I have already found 1.826 divided by 1.12. So I know what is this answer, and that is equal to 1.51. This answer plus QM. What is QM? It is 1.826. So this is equal to QH. So QH is equal to 3.336 kilojoule per second. So this is the way I have to solve problems based on Carnot cycle. We'll just see some simple problem and we'll close the session today. So this is a simple problem where the Carnot cycle is not specifically mentioned, but it is taken. So the 500 kgs of fruits are supplied to a cold storage room. Okay, supply to a cold storage. So the temperature, cold storage, as soon as I say cold storage, it is lower temperature, and that is equal to 20 degrees centigrade. Okay, so here you can see here 20 degrees centigrade is given. So what I have to do, I have to add 273 and make it into Kelvin. Okay, so here the cycles are not there. What it is doing, initially there is a 500 kgs of fruits, and the 500 kgs of fruits are at a temperature of 20 degrees centigrade, and the cold storage room is maintained at minus 5 degrees centigrade. So what is the in Kelvin? It is minus 5 plus 273. So that is equal to 263. It is 268 Kelvin. It is 273 and it is 260. So it is 268 Kelvin and it is 293 Kelvin. Now, what is the thing required? The fruits get cooled to the storage temperature in 10 hours. So what is happening? So in 10 hours, the temperature of the fruits are coming from 20 degrees to minus 5 degrees centigrade. So in 10 hours, the temperature is coming from 20 degrees to minus 5 degrees. So for finding that, what I need to find what is the specific heat of the food, of the fruits. The specific heat of the fruits is given as 1.5256. So this is the specific heat of the fruits. So if that is known, what I can do, 500 kgs of foods are supplied. Okay, 500 m, mass is 500, and this is the specific heat. And what is happening, the temperature of the foods are coming from 20 degrees to minus 5 degrees centigrade. So this is the temperature difference. So the amount of heat removed from the fruits in 10 hours, the amount of heat removed from the fruits in 10 hours is nothing but 15,700 kilojoules. Okay, so this is the amount of heat taken from the or removed from the fruits. So what is the second thing? So this is the amount of heat. It is 15,700. So the 15,700 kilojoules of heat is being removed from the fruits in 10 hours. So this is what we have calculated. So what is the next thing? So the total heat of freezing. So the total heat of latent heat of freezing. So m mass into latent heat is given. It will give the amount of heat removed for making them freeze. So at 0 degrees centigrade, what happens? All the food, it will become very solid. Okay, so that change in that state, the change in state, for change in state, what I have to do? So previous one is change in temperature. Now at this point, what I am doing is I am finding what is the heat extracted for change of the state from solid to the fruits will have some liquid content. So the liquid content is becoming solid content. For that change of state, what is the amount of heat that to be removed? So the amount of fruits that are supplied is 500 kg, and the latent heat of freezing of this fruit is 105 kg kilojoule per kg Kelvin. If I substitute, what I will get? I will get this value. What is that? It is 52,500 kilojoules. So there are two parts in this problem. So what are the two parts? One is there is a temperature change. The other one is there is a state change. So the temperature change you will do with CF or the specific heat, and the change of state is calculated using the latent heat of freezing. Okay, the latent heat of freezing of the food, that is equal to 105 kilojoule per kg, and the specific heat is nothing but 1.256 kilojoule per kg Kelvin. So the two aspects here are, one is to change the temperature from 20 degrees to minus 5 degrees, and in the process at 0 degrees centigrade there is a change of state that is happening, because the liquid, whatever liquid content in the fruits is becoming solid. So there is a state change, and in that at that time amount of heat removed is equal to this. So the net heat removed from the fruits is the heat removed for change of temperature, and heat removed for change of state. So that are for freezing. So if I add, so that is equal to 68,200 kilojoules. Now this kilojoules of heat is removed in 10 hours. Okay, it is removed in 10 hours. So what is the heat removed per minute? Okay, what is the amount of heat removed per minute? So it is equal to 68,200 divided by 10 hours, and each hour is having 60 minutes. So 10 divided by 10 into 60, I will get this 113.7 kilojoule per minute. Now the refrigeration capacity. So the refrigeration capacity is defined in terms of tons of refrigeration. Ton of refrigeration. Ton of refrigeration. So what is this ton of refrigeration? It is given as 210 kilojoule per minute. So this is the ton of refrigeration. 210 kilojoule per minute is the ton of refrigeration value. If I divide that with this 113.7, I mean the 113.7, if I divide with 210, I will get what is the capacity or what is the tonnage of the plant, how many tons of refrigeration it can supply. So that is equal to 0.541 tons of refrigeration, the capacity of the plant. So this is the additional point that we have discussed, the ton of refrigeration, which is the units of refrigeration, and that units of refrigeration is in kilojoule per minute. If I want to say, the value is 210 kilojoule per minute. Okay, so with this I close the session. Thank you. I am referring the textbook CP Aurora Refrigeration and Air Conditioning for the concepts that I am teaching in this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.